Look up at the night sky. Find the moon. Now imagine it gone. Not hidden behind clouds, not lost in city light. Gone. Erased from the sky as though it never existed. The tides flatten. The oceans grow still in a way they have never been still in 4 billion years. The shorelines, those thin, restless borders between land and sea, lose their daily rhythm. Creatures that evolved their entire biology around the rise and fall of water stand confused at the edge of a sea that no longer moves on any schedule they recognize. The calendars of ancient civilizations built around lunar phases become meaningless. The myths vanish. The festivals dissolve. The poets lose their oldest metaphor. That subtraction, quiet, total, devastating key, is not a thought experiment. It is history. There was a time deep in this planet's past when Earth had no moon. And the world that existed then was so foreign, so violent, so fundamentally different from the one you inhabit now, that calling it the same planet requires imagination most of us have never been asked to use. This is not a story about the moon exactly. It is a story about Earth, about what kind of world this planet was before a collision of almost incomprehensible scale rewrote everything. It is a story about how the world you know, the stable seasons, the reliable tides, the 24-hour days, the life that crawled from warm coastal pools and eventually became you. None of it was guaranteed. All of it traces back to a single event that could easily have never happened, and the strangest part of that story is this. The moon is not done shaping Earth. It is leaving. Slowly, silently, measurably. And what it leaves behind, over vast stretches of future time, may look more like the lost world that came before it than the world we recognize today. But we are getting ahead of ourselves. Stand on Earth for a moment. Look at what the moon quietly does without ever announcing itself. It pulls the oceans into tidal bulges, dragging billions of tons of water across entire ocean basins twice each day. Those tides have been carving coastlines, flooding estuaries, and cycling nutrients through shallow water ecosystems for billions of years. The intertidal zone, that narrow strip of rock and sand exposed and submerged in rhythmic alternation, may be among the most consequential environments in the history of life on this planet. The chemistry of early life, the first experiments of complex molecules finding shelter and concentration, may have played out in these zones precisely because something large and gravitationally powerful was circling overhead, pulling the water back and forth like a slow planetary breath. Remove the moon and those zones shrink to a fraction of their influence. Remove the moon and something even more fundamental changes. Earth's axial tilt, the 23.5-degree lean that gives you summer and winter, that makes the northern hemisphere cold in December and warm in July, that tilt is stabilized by the moon. Without it, the axis does not simply drift. It wobbles chaotically. Over hundreds of thousands of years, Earth's tilt could swing between extremes, reshaping climate zones so dramatically that no ecosystem could adapt quickly enough. Glaciers could sprawl to the equator. Deserts could form where oceans once sat. The slow, reliable predictability that complex life depends on would dissolve into something more like planetary-scale disorder. And the days, without the moon's tidal braking effect gradually slowing Earth's rotation across geological time, this planet would still be spinning near the speed it held in its earliest years. A day lasting roughly 6 hours. The sun rising and setting 4 times in what we now call a single day. Winds driven by rapid planetary rotation would tear across the surface with the ferocity no present-day weather system approximates. The atmosphere itself would behave differently, churning under dynamics incompatible with the biochemical patience that complex life requires. In that world, the slow unfolding of evolutionary history, the gradual accumulation of biological complexity across billions of years, might never have found stable enough ground to begin. The scientific model for how the moon came to exist carries a name that quietly understates its violence: the giant impact hypothesis. Approximately 4.5 billion years ago, a body roughly the size of Mars, a fully formed planet in its own right, named Theia, struck the young Earth at an oblique angle and at tremendous velocity. The collision did not merely crack the surface or gouge a crater. It partially vaporized both bodies. It ejected an enormous cloud of molten rock and metal vapor into orbit around what remained. Over thousands of years, that debris coalesced, cooled, and slowly became the moon. The Earth that survived was not the same Earth that had existed before the impact. It had a new rotation, a new tilt, a new companion in the sky, and the seeds of an entirely different future. What the impact erased, we can only partially reconstruct. The proto-Earth before Theia arrived had been forming for millions of years, accumulating mass, generating internal heat, perhaps developing a primitive atmosphere and some early form of surface water. That world died in hours. The crime scene is buried beneath 4.5 billion years of geological overwriting, beneath the oceans and continents and layers of convective history that followed. What remains are models, isotopic signatures in ancient rock, and a very large moon whose very existence demands an explanation. How many other planets in the universe, we have to wonder, went through their own early formation without ever receiving that explanation? How many worlds spun fast in chaos, tilted beyond the tolerance of life, and simply never steadied? That question has no easy answer, but it changes how you look at the moon rising tonight. Not as a permanent fixture, not as a given, as something earned through catastrophe and slowly, incrementally being lost. To understand the world that made you, we have to go back before it existed. To a molten earth spinning in darkness, to watch another world die so ours could live. Forget everything you know about this planet. Forget the blue marble suspended in dark space, the temperate oceans, the continental shelves worn smooth by billions of years of patient erosion. Forget the reliable progression of seasons, the 24-hour rotation, the axial lean that tilts one hemisphere toward the sun, while tilting the other away in a cycle so dependable that life built entire biological clocks around it. The Earth you are about to visit shares a location in space with the one you know. Almost nothing else is the same. We are approximately 4.5 billion years ago. The Sun exists, younger and roughly 30% dimmer than today, but recognizable. The inner solar system, however, is nothing like the ordered arrangement of planets we now map and name. It is a shooting gallery. Leftover debris from the disk of gas and dust that formed the Sun still traces chaotic orbital paths. Planetary bodies are still accumulating mass through collision, still defining their territories through gravitational dominance, still being deflected, captured, or destroyed by encounters with neighboring worlds. In this environment, the young Earth is not a finished product. It is an ongoing construction, violent and provisional, assembled from the wreckage of smaller bodies and continuously battered by those that haven't yet found a stable path. Step onto the surface, the ground beneath you, where there is ground, and there are wide stretches where this distinction barely holds. is not the layered silicate rock of the modern crust. Large sections are still partially molten. The earliest solid crust has formed in patches, cooled where heat has had just enough time to dissipate. But the interior of this planet is so hot, so energetically convective, that the surface is not stable in any long-term sense. Volcanic activity does not operate here the way it operates on the modern Earth, punctuating geological time in occasional eruptions. It is continuous, pervasive, a fundamental feature of the landscape rather than an interruption of it. Vast plains of cooling basalt stretch between pools of still liquid rock that glow orange and red at the margins. The sky above is thick, not with the nitrogen-oxygen atmosphere you breathe, but with a dense mixture of water vapor, carbon dioxide, methane, and sulfur compounds outgassed from the interior. Light reaches the surface but diffused, filtered through a high-pressure atmospheric column that sits heavier than any air on modern Earth. Now watch the sky. This is where the first Earth becomes most disorienting, most viscerally alien. The sun moves. It moves at a speed that takes a moment to register as real. Because this Earth is spinning nearly 4 times faster than the one you know, a full day, one complete rotation, lasts somewhere around 6 hours. The sun does not arc slowly across a long, graduated sky. It rushes. Shadows swing through their full rotation, not over the course of 12 hours, but in 3. Temperature patterns that on modern Earth build gradually across a full day's heating cycle, that warm the land and drive the complex circulation of atmosphere and ocean, have no such opportunity here. The atmosphere heats and cools in compressed pulses. Wind patterns driven by rapid planetary rotation and extreme temperature differentials whip across the surface with intensities that no present-day weather system quite captures. There is no calm season on this world. There is no restful equinox. There is only the relentless, rapid alternation of brief, intense heating and brief, fierce cooling, hour after hour, cycle after cycle. And then there is the tilt. On the Earth, the axial tilt, that 23.5-degree lean of the planet's rotational axis relative to its orbit around the Sun, is essentially stable. Not perfectly fixed, but constrained within a narrow range over tens of thousands of years, gently cycling between roughly 22 and 25 degrees. This stability is not accidental. It is maintained at least in part by the gravitational influence of a large nearby mass, the Moon. Remove the Moon and the situation changes fundamentally. Without that stabilizing torque, Earth's axial tilt does not hold to its familiar range. The mathematical models that describe rotational dynamics in the absence of a large natural satellite suggest that tilt can migrate widely and unpredictably over geological timescales, potentially swinging from near zero, where the planet would have almost no seasons, to extreme angles that would tilt polar regions directly toward the sun for months at a time and plunge them into equally long complete darkness. Entire climate zones would not merely shift, they would lose any long-term identity at all. The reliable geography of habitability, equatorial warmth, polar cold, temperate middle latitudes, would be replaced by a climate system lurching between configurations incompatible with the patient, multi-generational processes that complex life requires. Look at Mars, not as a cautionary tale exactly, but as a data point. Mars has no large moon. Its axial tilt has wandered across a range far wider than Earth's over its history, contributing to conditions that may have dramatically altered or ended whatever early promise its wet surface held. Mars is not Earth, and its story is its own, but the comparison is useful. A world without a significant lunar stabilizer is a world with a less predictable rotational history and, in consequence, a less predictable long-term climate. The Earth without the Moon is a version of that problem on a potentially larger scale with higher stakes, because the early Earth had everything the first chapters of complex life might need: liquid water, carbon chemistry, energy, except the one thing that might have let those chapters extend into something genuinely elaborate. Was there water on this early Earth? This question has occupied geochemists for decades, and the answer increasingly is yes, though the word ocean requires careful handling. Evidence from ancient zircon crystals, among the oldest solid material preserved anywhere on Earth, hints that liquid water existed at the surface within a few 100 million years of the planet's formation, possibly earlier. Where that water came from is still actively debated. Some arrived in the bodies of water-rich asteroids and comets during the period of heavy bombardment that scarred the inner solar system in its early history. Some may have been present in the materials from which Earth originally accreted. But whether this water formed coherent, stable oceans in the modern sense, or existed in a more transient, turbulent relationship with the surface, cycling rapidly between liquid and vapor as volcanic heat and atmospheric pressure fluctuated, is a question the evidence does not yet answer cleanly. What it does suggest is that this early Earth had the chemical ingredients for complexity. What it lacked was stability. And stability, it turns out, is not a luxury condition for life. It is a prerequisite for the kind of life that goes anywhere interesting. Think about what prebiotic chemistry requires. The molecules that would eventually underwrite biology, the amino acids, the nucleotides, the lipid precursors, need environments where concentration can occur, where reactions can proceed over extended time, where products are not immediately destroyed by the same energy that drives them to form. Hydrothermal vents in the ocean floor provide one such environment. Tidal pools provide another. The intertidal zone, that narrow, rhythmically flooded band at the edge of sea and land, is among the most chemically productive environments for early molecular complexity, cycling between wet and dry states in ways that concentrate, react, and redissolve chemical systems with extraordinary regularity. But tidal pools depend on tides, and tides, in their full planetary scale majesty, depend on the moon. The sun generates tides too, it still does. But the solar tidal effect on Earth is roughly half the lunar contribution. Without the moon, solar tides exist. They are modest, slow, and locked to the already rapid solar day of a fast-spinning Earth. The dynamic range of intertidal exposure, the ecological complexity of the zone itself, is a shadow of what the moon would later make possible. This is what science is slowly assembling: a picture of the pre-impact Earth as a world in draft form. Not a dead world, not a sterile world, but an unfinished one, missing a fundamental architectural element, turning so fast that its climate couldn't breathe, tilting too freely for any long-term pattern to hold, generating tidal forces too weak to fully exploit the chemistry simmering at the meeting point of land and sea. The first Earth had raw materials and energy in abundance. What it did not yet have was an editor. The idea that a planetary collision could function as an act of cosmic editing, that the most violent event in Earth's 4.5 billion year history was also, in some measurable sense, a creative act, is one of those ideas that sits uncomfortably between catastrophe and design without belonging entirely to either. It does not require intention to be true. It simply requires that the outcome of the collision, evaluated across billions of subsequent years, produced conditions significantly more favorable to complex life than what existed before it. And by nearly every parameter we can measure, rotation rate, axial stability, tidal amplitude, atmospheric evolution, the evidence quietly accumulates in that direction. But we are still standing on the first Earth, still watching the sun race across a thick, hot sky, still feeling the ground shift beneath us where convection hasn't yet been fully tamed by cooling. Somewhere in this young solar system, on an orbital path that has been quietly closing in since the disk first condensed, another world is moving through space. It is not small. It is not drifting. It is on a trajectory that, over the next hundreds of millions of years, will bring it into a proximity that neither it nor the Earth will survive unchanged. The solar system is littered with the trajectories of bodies that never found a stable path. Most of them collided with something, were ejected, or drifted into the outer dark. This one had an appointment. In this cosmic shooting gallery, Earth did not move alone. Another world was on a collision course. And it had a name. Theia. Before the collision, there was another world. This is the part of the story that tends to get lost in the spectacle of what follows. The part that deserves a moment of stillness before everything accelerates into violence. Theia was not an asteroid. It was not a rogue boulder tumbling through an undifferentiated solar system. It was a planet, a fully formed, gravitationally organized planetary body approximately the size of Mars, which means it was approximately half the diameter of Earth and carried a mass somewhere around 10% of Earth's current total. It had existed long enough to undergo the process that turns an undifferentiated rocky mass into a structured world, differentiation. Under its own internal heat, heavier elements, iron, nickel, had sunk toward its center, forming a metallic core. Lighter silicate materials had risen, forming a mantle and an early crust. Whether Theia had an atmosphere, whether liquid water had briefly existed on its surface, whether any of the early chemical experiments that precede biology had begun within it. These questions are beyond what current evidence can answer. But they are not beyond what current evidence permits us to ask. Theia was complex enough, structured enough, and old enough that the answer might not be no. The solar system, in its early hundreds of millions of years, was populated with such worlds. The current 8 planets are survivors. The vast majority of planetary embryos that formed from the solar disk were not so fortunate. They collided with larger bodies, were gravitationally ejected into interstellar space, or were accreted into the growing masses of the planets that remained. Theia was, in this sense, an ordinary casualty of an extraordinarily violent epoch. What made its destruction extraordinary? What separated it from the countless anonymous collisions of the early solar system? Was what it left behind. The trajectory that brought Theia to Earth had been developing for a long time. In the models scientists used to reconstruct early solar system dynamics, a body of Theia's mass forming in the inner solar system would have occupied a gravitationally unstable position. The gravitational influences of the growing Jupiter, the interactions with other planetary embryos, and the complex orbital resonances of the young system would have perturbed its path over millions of years, nudging it into an increasingly eccentric orbit. Not suddenly, not dramatically, just incrementally, the way compound interest quietly transforms an initial amount. until one day the trajectory that seemed safely clear of Earth was no longer safely clear of Earth. The two worlds had, in a sense, been drifting toward each other for millions of years. The collision itself was simply the final millisecond of that long, slow approach. The impact did not happen at the speed of a rifle bullet. It happened at the speed of a planet. Current models, refined over decades of computational simulation, suggest Theia struck the proto-Earth at somewhere between 15 and 40 kilometers per second, a velocity so far outside ordinary human reference that it almost loses meaning. At the lower end of that range, the kinetic energy released in the collision exceeded the gravitational binding energy of the entire Earth, which means the energy of impact was not merely sufficient to melt the surface, or gouge an enormous crater, or vaporize the oceans. It was sufficient in principle to disrupt the entire planet. The fact that Earth survived as a coherent body is itself a product of the specific conditions, angle, velocity, mass ratio, under which the impact occurred. That angle is crucial to the story. The simulations that best reproduce the moon we actually observe, its mass, its composition, its orbital characteristics, consistently favor an oblique impact rather than a head-on collision. Theia did not strike the proto-Earth like a hammer driving a nail. It struck at an angle more like a glancing blow, the kind that transfers angular momentum as well as energy. This geometry matters enormously. A direct head-on impact at similar velocity would likely have either shattered both bodies into a debris field, to disperse to coalesce into a stable moon, or merge the two planets so completely that little material would have been ejected into orbit at all. A highly oblique, grazing impact might have sent Theia skipping off into a new trajectory without sufficient mass exchange to build a moon. The impact that produced our moon threaded a path between these failure modes, oblique enough to eject a massive debris disk into orbit, energetic enough to significantly alter Earth's rotation and tilt, but not so catastrophic as to simply unbind the system entirely. What followed the moment of contact is almost impossible to frame in familiar terms. The collision was not instantaneous in the way that word implies. Not a flash and a shockwave. It played out over minutes and then hours on a planetary scale. When Theia's leading edge contacted the proto-Earth's mantle, the energies involved were sufficient to immediately vaporize rock. Not melt it, vaporize it. The contact zone became a region of rock plasma, minerals converted directly into their constituent ions and electrons, at temperatures that exceed any natural process currently occurring on Earth's surface. That plasma expanded outward and upward. Theia's mantle continued driving forward as its leading edge was destroyed, the collision propagating through the bodies of both planets as a shockwave traveling through material that was being continuously transformed by the passage of the wave itself. In the first minutes, Theia's core plunged deep into the proto-Earth's interior. Some of it merged with Earth's existing core. Some of the outer portions of both mantles, already partially vaporized, began moving outward from the impact zone at velocities that exceeded Earth's escape velocity. But not by much, and not everywhere. This is where the moon comes from. Not from a single dramatic ejection, but from an extended process of material being launched into trajectories that kept it in orbit around the new, transformed Earth. Some of that material was above escape velocity and departed the system entirely, lost to space. Some fell back to Earth, contributing to a magma ocean that now covered the entire planetary surface. But a significant portion, the portion the moon is made of, achieved orbital velocities. It spread into a disk of molten rock and rock vapor, encircling the Earth at distances ranging from near the surface to several Earth radii. This disk was not stable in its initial form. It was turbulent, collisional, hot, and rapidly evolving. Within hundreds to thousands of years, a geological eye blink, the particles within the disk began accreting. Small clumps formed, collided, merged, and grew. Angular momentum was redistributed through these collisions, gradually organizing the disk into a smaller number of larger bodies. Within perhaps 100 years of the initial impact, something that could be called the proto-moon had emerged from the disk. Within a few thousand years, it had swept up most of the remaining debris into its growing body. The moon was born. Consider how easily it could have been otherwise. The scientists who model this impact do not do so with a single simulation. They run thousands of them, varying the parameters, impact angle, velocity, mass ratio, internal structure of both bodies, across their plausible ranges, and they examine what comes out the other side. What they find is a distribution of outcomes, not a single inevitable result. Many simulations produce no stable moon at all. The debris is too dispersed, or the angular momentum budget is wrong, or the largest accreted body ends up in an unstable orbit and either crashes back into Earth or escapes entirely. Some simulations produce two moons, a large primary and a smaller companion that later collides with it. Some produce a moon too small to provide significant tidal forcing or axial stabilization, a companion that exists but doesn't do the work our moon does. The outcome that matches our actual moon in terms of mass, orbital characteristics, and isotopic composition requires parameters that are entirely physically plausible but by no means dominant across the simulation space. This event was possible. It was perhaps even probable given the right initial conditions. But it was not the only thing that could have happened. The question of what the moon is made of carries one of the most beautiful and quietly unsettling discoveries in modern planetary science. When researchers compare the isotopic composition of lunar rocks, brought back by the Apollo missions and analyzed in laboratories across several decades, to the isotopic composition of Earth rocks, they find something unexpected. The moon and Earth are isotopically nearly identical, not similar, nearly identical, in ratios that differ from almost every other body in the solar system. Meteorites from different parts of the solar system carry distinct isotopic signatures, fingerprints of the region where they formed. Mars has its own signature. The asteroid Vesta has its own, but the Moon and Earth share theirs almost completely. This finding, which initially seemed to support the simplest version of the giant impact hypothesis, has actually complicated it. If Theia formed elsewhere in the solar system, as many models suggest, it should have had a different isotopic signature. And the Moon, which in many simulations is composed predominantly of Theia's mantle material, should reflect that difference. The fact that it doesn't has forced refinements to the model. Perhaps Theia formed in roughly the same region of the solar system as Earth, and therefore shared its isotopic heritage. Perhaps the impact was energetic enough to thoroughly mix the two mantles, homogenizing any original isotopic differences. Perhaps the Moon contains more Earth material than earlier simulations suggested. The isotopic data is not an argument against the giant impact hypothesis. It remains the model that best explains the full range of evidence. But it is a reminder that the story is not entirely closed. The Moon is still telling us things about its own origin that we are still learning to read. What emerged from the impact was a transformed system. The proto-Earth, now merged with a significant fraction of Theia's mass, had been partially vaporized, entirely melted, and fundamentally reorganized. Its rotation had changed. The angular momentum transferred by the oblique impact had altered the planet's spin rate and reoriented its axis. The new Earth was different from the old one in ways that were not cosmetic. It now had a companion in orbit, still close, still immense in the early sky, radiating back heat onto a surface that was itself a global magma ocean. The system was catastrophically unstable in the immediate aftermath, but it was unstable in a direction that led somewhere. Two bodies, a primary and its satellite, governed by the same gravitational relationship that would, over billions of years, gradually transfer angular momentum from Earth's rotation to the Moon's orbit, push the Moon slowly outward, slow Earth's spin, and build the tidal architecture that liquid water life would eventually find so useful. From a certain perspective, the birth of the Moon is the most important event in Earth's history after the formation of the planet itself. Not because of what it destroyed, though it destroyed plenty, but because of what the destruction made possible. The first Earth was a draft. Theia's impact was not a catastrophe that interrupted a promising trajectory. It was a revision that made the trajectory possible in the first place. Out of fire and ruin came a new kind of world, an Earth with a moon. But what did that actually change? Every morning, without thinking about it, you experience the most consequential aftershock in Earth's history. The sun rises. It does so approximately every 24 hours, give or take a handful of seconds depending on the time of year. That rhythm, the alternation of day and night across a cycle of almost exactly 24 hours, feels so fundamental, so built into the architecture of living things, that it registers as a universal constant rather than a historical contingency. It is not. The length of your day is not a given. It is a consequence. And the thing that produced it is the same collision that spent the last section reducing two planets to plasma. When the debris from the Theia impact coalesced into the early Moon, and the transformed Earth settled into its new configuration, the day was not 24 hours. It was somewhere in the range of 5 to 6 hours. The impact had transferred angular momentum to the Earth-Moon system, had in effect set both bodies spinning in a new relationship, and the planet was moving fast. This is not a minor difference from the world you know. It is a fundamentally different rotational regime with cascading consequences for almost every physical process that runs on the surface of the planet. A 6-hour day means the sun rises and sets 4 times in what we now call a single day. It means the atmosphere, heated by a fast-moving sun, never has time to develop the deep, slow circulation cells that govern modern climate patterns. It means the temperature differential between day and night, instead of accumulating gradually across 12 hours of solar heating and 12 hours of radiative cooling, is compressed into a few hours on each side. Sharp, intense swings rather than the gradual tide of warmth and cool that modern ecosystems are built around. It means the Coriolis effect, driven by Earth's rotation, operates more powerfully, generating wind systems more vigorous and more chaotically distributed than anything in the current atmospheric record. This was not a world friendly to stability. It was a world designed by its physics to make stability difficult. The Moon began changing that immediately, not quickly. Nothing at geological scale happens quickly, but relentlessly in a direction that mattered enormously for everything that came after. The mechanism is tidal friction. As the moon's gravity pulls on Earth's oceans and to a lesser degree on its solid body, it raises tidal bulges, regions where the gravitational pull is slightly stronger and matter is drawn upward or outward. These bulges are not static. Earth's rotation carries them slightly ahead of the moon's orbital position because Earth rotates faster than the moon orbits. The result is a gravitational imbalance. The tidal bulge that runs slightly ahead of the moon pulls the moon forward in its orbit, gradually transferring rotational energy from Earth's spin into the moon's orbital energy. The moon accelerates slightly and drifts outward. Earth slows. This process has been running continuously since the moon formed, and its cumulative effect over 4.5 billion years has lengthened the day from roughly 6 hours to the 24 we now inhabit. Ancient coral fossils, which record daily growth rings within annual bands, suggest that 400 million years ago the year contained approximately 400 days, each one shorter than our current 24 hours. The moon has been working on this problem for a long time, and it is not yet finished. Each year the day grows longer by a small fraction of a second. Each year the moon moves approximately 3.5 centimeters farther from Earth. The system is still evolving, still transferring energy along the gravitational bridge that connects the two bodies. The lengthening of the day was not by itself enough to transform Earth's climate, but it contributed to a cumulative change in the rotational dynamics of the planet that had profound downstream effects. A slower rotation means a weaker Coriolis effect, which means the large-scale circulation of the atmosphere organizes into fewer, broader, more stable cells. It means the equator to pole temperature gradient can drive atmospheric circulation in more predictable, less chaotic patterns. It means the day-night temperature cycle, spread across a longer period, has time to develop the kind of gradual thermal variation that evaporation, precipitation, and weather systems need to run their cycles properly. None of this happened overnight. The transition from a fast, chaotic rotational regime to the relatively moderate one we now inhabit took billions of years and occurred across geological epochs of continuous, incremental change. But the direction of that change was set by the moon's gravitational interaction with Earth from the moment the impact debris coalesced into a coherent satellite body. The moon was the engine. The day length was the output. The climate was the consequence. Then there is the tilt. Your 23.5-degree axial lean, the one responsible for every summer and winter you have ever experienced, is maintained in a stable range by the moon's gravitational influence on Earth's rotational bulge. Without that influence, the mathematical description of Earth's rotational dynamics changes significantly. The obliquity, the angle between Earth's axis and the perpendicular to its orbital plane, is subject to gravitational perturbations from other planets, primarily Jupiter and Saturn, whose gravitational influence reaches across the solar system and nudges Earth's orbital and rotational parameters over astronomical timescales. On a moonless Earth, these perturbations have no large nearby stabilizing torque to constrain them. The tilt is free to migrate across a much wider range. Computational models of moonless Earth rotational dynamics suggest obliquity could vary between nearly zero and values approaching 60 degrees or higher, following chaotic trajectories that depend sensitively on initial conditions. This is not a slow, predictable oscillation. It is a system capable of wandering into configurations that would be climatically unrecognizable from the present. Mars offers a concrete illustration of what this looks like in practice. Mars has two moons, but both are tiny, captured asteroids that provide essentially no meaningful stabilizing torque to the planet's rotational axis. Mars's obliquity has varied between roughly 10 and perhaps 60 degrees over its history, and this variation has left measurable marks on its surface. Layered polar deposits that record alternating climate cycles, evidence of ice sheets that advanced and retreated on timescales, and to extents inconsistent with the mild obliquity variations Earth experiences. The relationship between Mars's wandering tilt and its increasingly hostile surface environment is not simple or monocausal, but the absence of a stabilizing large moon is part of the story of why Mars, which may once have had liquid water at its surface, became the frozen desert it is today. Earth, by contrast, has kept its tilt within a relatively narrow range for billions of years. The seasons change. The climate oscillates between ice ages and warmer interglacials on timescales driven by orbital cycles. But the envelope of that variation is constrained enough that complex ecosystems, which require generational stability to build the elaborate food webs and evolutionary dependencies that advanced life depends on, can persist and deepen over geological time. Consider what a wandering tilt would mean for a developing biosphere. An obliquity oscillation that drove Earth's axis to extreme angles over hundreds of thousands of years would not merely inconvenience the ecosystems that had developed under moderate tilt, it would destroy them. Tropical regions at high obliquity receive less average annual sunlight than polar regions, fundamentally reversing the latitudinal temperature gradient that drives atmospheric and oceanic circulation. Polar regions, receiving months of continuous sunlight followed by months of complete darkness, develop extreme seasonal swings incompatible with most complex organisms. The long-term evolutionary project of building complexity, the slow accretion of biological innovation across millions of generations, requires that the ground stay under your feet in a climatic sense. A planet whose axial tilt drifts unpredictably cannot offer that ground. The moon, by damping the range of Earth's obliquity variations, did not merely make Earth more comfortable. It may have made the sustained evolutionary continuity that leads to complexity possible at all. And then there are the tides, not the modest tides of the modern ocean, which raise and lower sea level by a meter or two at most locations, which are predictable to the minute for centuries in advance, which are woven so thoroughly into coastal ecosystems that every organism living between the high and low tide marks has evolved its entire life cycle around them. The early tides, when the moon was young and close, were nothing like these. When the moon first formed, it was orbiting at a fraction of its current distance from Earth, perhaps as close as 10 to 20 Earth radii compared to the roughly 60 it currently occupies. Tidal forcing scales with the inverse cube of distance, which means the tidal effect of an early moon at 1/3 its current distance was not 3 times stronger. It was 27 times stronger. The tidal bulges raised in the early ocean were immense. On a coast anywhere near the equatorial regions, tidal flooding events would have driven water far inland and retreated far out to sea, cycling on whatever period the early moon's orbit determined, exposing and inundating coastal zones at amplitudes that dwarf anything in the present geological record. This is the tidal pump. The concept has gained significant traction in origin of life research over the past several decades, and its central logic is elegant. Prebiotic chemistry, the chemistry that precedes biology, the chemistry that assembles simple molecules into the more complex structures that eventually become life, requires concentration. Dilute chemistry in an open ocean spreads its reactants too thin for most interesting reactions to occur reliably. But in an intertidal zone, the rhythmic flooding and recession of water does something chemically useful. It concentrates. As the tide retreats, pools of water left behind evaporate, increasing the concentration of dissolved organic molecules. Minerals in the exposed rock catalyze reactions between those molecules. When the tide returns, it refreshes the chemical pool, delivers new reactants, and washes away some reaction products, preventing the system from reaching equilibrium and stopping. This cycle, wet and dry, concentrated and diluted, heated by the sun and then refreshed by ocean water, is essentially a natural chemical reactor with the built-in stirring mechanism powered by orbital mechanics. The stronger the tides, the larger and more dynamic the intertidal zone. The larger and more dynamic the intertidal zone, the more chemical processing occurs across its breadth. In the early Earth's vast intertidal zones, driven by a moon far closer and far more gravitationally dominant than today's, the scale of this natural chemistry was enormous. Life did not necessarily start in a tidal pool. The question of where exactly the chemistry of biology originated, whether in hydrothermal vents on the ocean floor, in surface pools in atmospheric chemistry, or in some combination, is genuinely open. But the tidal pump hypothesis is taken seriously precisely because the physics of the early moon's tidal forcing maps so cleanly onto the chemical requirements of prebiotic synthesis. Concentration, cycling, mineral catalysis, and regular refreshment of chemical gradients are all things that strong tidal zones provide in abundance. And whether or not tidal zones were the specific nursery of the first self-replicating chemistry, they were almost certainly critical environments for the diversification and spread of early life once it had emerged. The intertidal zone is an interface between sea and land, between aquatic chemistry and terrestrial chemistry, between the stable conditions of the ocean depths and the variable energetically rich conditions of the exposed surface. Interfaces in complex systems tend to be places where interesting things happen. The moon made that interface as wide, as dynamic, and as chemically productive as it could possibly be. The three pillars, spin, tilt, tides, do not operate in isolation. They are interlocked, each reinforcing the others in building a planetary environment with the specific characteristics that sustained complexity requires. A slower rotation moderates climate and makes weather patterns more predictable. A stabilized tilt keeps the latitudinal temperature gradient from collapsing into chaos. Powerful tides create the chemical processing environments where the early experiments of life could accumulate, diversify, and eventually venture from the water's edge onto land. Take any one of these away, and the remaining system is less hospitable, less stable, less capable of sustaining the long, patient, generational work of evolution. Take all three away, and you have the first Earth again. Fast, chaotic, tidally weak, and tilting freely through configurations that no ecosystem could track. You are a consequence of a particular spin rate, a particular tilt, a particular tidal rhythm. Not metaphorically, literally, the biochemical machinery that runs in your cells, the oxygen in your atmosphere, the stable temperate zones where complex terrestrial life evolved across hundreds of millions of years. All of it downstream of the moon's invisible governing work on the physics of this planet. Every morning when the sun rises, it does so at the speed it does because a Mars-sized world died here 4.5 billion years ago and left a gravitational companion that has been slowing us down ever since. Here in the rhythm between water and air, something astonishing began. Under the moon's pull, chemistry became biology. Life did not arrive on Earth fully formed. It assembled itself, molecule by molecule, in conditions that we are still working to fully reconstruct, over a timescale so vast that the entire history of complex animal life, everything with a backbone, everything you might recognize as a creature, occupies only the final fraction of the story. The earliest evidence for life on Earth reaches back somewhere between 3.5 and 4 billion years, in the form of chemical signatures and microfossil structures preserved in ancient rock formations. These first organisms were simple by any structural measure, single cells without nuclei, running on chemistry that would be unrecognizable as biology to anyone who learned the subject only from textbooks describing the elaborate cellular machinery of modern life. And yet they were alive. They metabolized. They reproduced. They responded to their environment. Somewhere in the chemistry of the early Earth, in the hydrothermal systems, in the mineral-rich coastal zones, in the tidal flats, where concentrated organic molecules cycled between wet and dry under the influence of a moon that then loomed far larger in the sky than the one we know. The threshold between complex chemistry and the simplest biology was crossed. We do not know exactly where, we do not know exactly how, but we know when, and we know what kind of world was present when it happened. A world already being shaped, already being stabilized, already being organized by the gravitational partnership between Earth and its recently formed companion. The early moon was not the modest silver disk of modern myth and poetry. When life was first assembling itself in Earth's oceans, the moon was close enough that its apparent diameter in the sky may have been several times larger than what we see today. Its tidal influence on the young Earth's oceans was correspondingly enormous. The intertidal zones of the Archean Earth, that geological eon stretching from approximately 4 billion to 2.5 billion years ago, were not the narrow, gently fluctuating strips of coastline that today's beaches represent. They were wide, dynamically flooded and exposed plains where the chemistry of the shallow sea met the mineral surfaces of exposed rock and the energy input of direct sunlight. In these zones, organic molecules were not simply reacting. They were being processed through repeated concentration cycles, dried and re-wetted, heated and cooled, catalyzed by mineral surfaces and exposed to ultraviolet radiation that the early atmosphere, lacking the oxygen-based ozone layer that later life would build, did not effectively block. Whether the first self-replicating molecules emerged in these zones or arrived there from some other origin, the tidal flat was an extraordinary processing environment, energetic, chemically rich, and rhythmically active in ways driven directly by the moon's orbital mechanics. The earliest microbes that left fossil records appear to have been photosynthetic or chemosynthetic, extracting energy from sunlight or from chemical gradients in their environment. What is striking about even these earliest organisms is evidence that they were already responding to rhythms. The day-night cycle, the alternation of light and dark on the now longer but still short day of the early Earth, was written into the chemistry of life almost from the beginning. The protein machinery that modern cells use to track the circadian cycle, to anticipate sunrise and prepare their metabolic processes accordingly, appears to be among the most ancient and conserved biological mechanisms we know. It predates the divergence of the major domains of life. It is found in recognizable form in bacteria, in archaea, in fungi, in plants, and animals. This universality is not coincidental. The day-night cycle was the most reliable, most energetically significant, most evolutionarily consistent environmental signal available on early Earth. Life learned to read it, and that learning became structural, not behavioral in the flexible way of learned responses, but molecular, written into the chemical architecture of the cell itself. The moon's cycle was not far behind. 29.5 days, the synodic period of the moon, the time from one full moon to the next, is registered in the biology of organisms that have never, in evolutionary terms, had any reason to track the moon except that the moon's cycle governed the tides and the tides governed their habitat. Intertidal organisms evolved their reproductive and behavioral timing around lunar phases because the flooding and exposure of their environment was itself modulated by the moon. The spring tides of new and full moons, when the sun and moon align their gravitational pulls, produce the most extreme tidal ranges. The neap tides of the quarter moons produce the most moderate. Organisms whose reproduction depended on reaching maximum tidal depth, on accessing normally exposed surfaces, or on synchronizing with the flooding and exposure of specific zones learned, through the brutal efficiency of natural selection, to time their cycles accordingly. That timing is not learned behavior in individuals. It is encoded biology, replicated faithfully across generations, reflecting billions of years of the moon's gravitational governance of the littoral zone. Coral reefs, among the most complex and productive ecosystems on Earth, spawn in mass events that are precisely timed to lunar cycles. In tropical reef systems worldwide, corals release their eggs and sperm in synchronous events that occur on specific nights following a full moon in particular months. The synchronization is so precise, so coordinated across entire reef systems spanning hundreds of kilometers, that it can only be explained by a shared external signal strong enough to entrain the reproductive clocks of millions of individual animals simultaneously. That signal is the moon. Its light, its gravitational influence on tidal patterns, its phase-dependent modulation of water temperature and chemistry, all of these contribute to a signal that complex organisms have been reading and responding to for hundreds of millions of years. The reef's mass spawning event is not a curiosity. It is a living record of the moon's deep integration into the timing architecture of complex life. Consider what was required for that complexity to develop at all. The trajectory from the first self-replicating molecules to a coral reef is not simply a matter of chemical elaboration over time. It required sustained environmental continuity across geological timescales. It required that the conditions hospitable to complex multicellular life, moderate temperatures, liquid water, adequate oxygen, stable enough climate to allow the accumulation of ecological complexity across millions of generations, persist long enough for the slow, stepwise accumulation of evolutionary innovation to do its work. The major evolutionary transitions that mark the history of life on Earth, the origin of the eukaryotic cell, the emergence of multicellularity, the Cambrian explosion of complex body plans, the colonization of land, the rise of endothermy in birds and mammals, all of these required not simply favorable conditions at a single moment, but continuity of conditions across the immense timescales that natural selection requires to produce genuinely novel structures. The moon's stabilization of Earth's axial tilt did not directly cause any of these transitions, but it maintained the climatic envelope within which they were possible, kept the latitudinal temperature gradient consistent enough, the seasonal cycle regular enough, the long-term progression of ecological opportunity steady enough for complexity to accumulate rather than be periodically reset by catastrophic climatic reorganization. This is a quiet, difficult kind of contribution to acknowledge. We find it easier to assign importance to dramatic events. The asteroid impact that ended the Cretaceous, the volcanic episodes that caused the great extinctions, the ice ages that reshaped continents and drove speciation. The moon's contribution is the opposite of dramatic. It is the absence of chaos, the stability that allowed a billion years of quiet microbial diversification to give way to the Cambrian's explosion of complex forms. The regularity that allowed ecosystems to build their elaborate networks of dependence and cooperation across geological time without being periodically dismantled by planetary-scale climatic reorganization. In a universe full of rocky planets orbiting within their stars' habitable zones, this kind of deep continuity may be rarer than the simple presence of liquid water. It may require something like a moon. The moon's rhythm eventually found its way into organisms that had no ocean to track, no tidal flat to navigate, nocturnal animals whose behavior is modulated by moonlight intensity, whose predator-prey dynamics shift with the lunar phase, whose migration timing is influenced by the availability of lunar illumination. These organisms were shaped not by the tides directly, but by the same 29-day clock that the tides had been running for billions of years. The moon entered the behavioral ecology of terrestrial life without changing the mechanism. It was still the same orbital period, the same gravitational partnership with Earth, producing now a different proximate signal, light rather than tidal movement, but routed through the same ancient biological response systems that the intertidal world had already built. The human relationship with the moon is, from this perspective, neither mystical nor accidental. The calendar systems of virtually every pre-modern civilization were organized around lunar cycles because the moon's phase was the most reliably observable periodic signal in the sky before the development of sophisticated astronomical instruments. Agricultural timing, religious ritual, social coordination. The lunar month provided a natural unit of organization for complex societies precisely because it had already been providing a natural unit of organization for complex biology for hundreds of millions of years before humans appeared. When the Babylonians divided the year into lunar months, when the Islamic calendar retained the lunar year against the drift of seasons, when Stonehenge's builders aligned their monuments with lunar standstills, they were not inventing a relationship with the moon. They were formalizing one that their biology had been maintaining since long before their species existed. There is something vertiginous about following that thread all the way back. The molecular clock in your cells that tells you when to sleep and when to wake. The one that still runs on a roughly 24-hour period, even in complete darkness. The one that jet lag disrupts by forcing it out of synchrony with the external day-night cycle. That clock is an inheritance from organisms that lived in the tidal zones of the early Earth, under a moon that was then far closer than the one you see tonight. The periodicity built into your cellular biology is a fossil record of the moon's long relationship with life on this planet. Not a metaphor for that relationship, a direct material consequence of it, preserved in molecular form across 4 billion years of continuous evolutionary descent. The Apollo astronauts who walked on the moon in 1969 were not simply explorers reaching a distant destination. They were matter that had been ejected from Earth's mantle 4.5 billion years earlier in the Theia impact, subsequently reorganized by 4 billion years of chemistry and evolution into organisms complex enough to understand the history of the place they were visiting, and then transported back to the surface of the object formed from that original ejection, The moon landing was, in a precise geological sense, Earth material returning to the moon, the closed loop of a collision finally completing itself across deep time. The footprints left in the lunar regolith were made by creatures whose existence depended on the collision that made the moon, walking on the surface of the object the collision created. We are the first part of the Earth-Moon system to understand itself, and to realize that this partnership is not forever. The moon is leaving. Not dramatically, not in any way you could detect across a human lifetime, not with any urgency that registers against the backdrop of ordinary experience, but measurably, verifiably, in numbers confirmed by laser beams bounced off reflectors left on the lunar surface by Apollo astronauts, and measured to millimeter precision from observatories on Earth. The moon is moving away from us at approximately 3.8 centimeters per year. That is roughly the rate at which your fingernails grow. It is, by any human standard, an imperceptible drift. By astronomical standards, it is a planet leaving. The mechanism is the same one that has been operating since the moon formed: tidal friction. Earth's rotation carries the tidal bulges raised by the moon's gravity slightly ahead of the moon's orbital position. The gravitational interaction between this displaced bulge and the moon pulls the moon forward, increasing its orbital energy and pushing it to a higher, wider orbit. Every tide that rises in Earth's oceans, every tidal bulge that forms and propagates across ocean basins under the moon's gravitational pull, transfers a small increment of Earth's rotational energy into the moon's orbital energy. Earth slows. The moon recedes. The transaction is continuous and, at the level of physics, perfectly described by the conservation of angular momentum. There is no mechanism that reverses it. There is no restoring force that will eventually pull the moon back. The drift is asymmetric and irreversible on any timescale relevant to life, to civilization, or to the biological future of this planet. The moon will not return. It will simply continue moving outward until external forces, the eventual evolution of the sun, the long-term dissipation of the system's energy, bring the story to a different kind of conclusion. Project this forward, not by 1,000,000 years, which is too short to matter much. Not by 10 million, which is still geologically modest. Project it by hundreds of millions of years, by the kind of timescales across which the geological and biological history of Earth is actually written, and the consequences accumulate into something profound. In roughly 200 million years, if the current rate of recession continues without significant change, the moon will be measurably smaller in Earth's sky than it is today. Total solar eclipses, those extraordinary coincidences of geometry in which the moon's apparent diameter precisely matches the sun's, allowing the solar corona to blaze out around a perfect dark disk, will cease to be possible. The moon will have shrunk, in angular terms, to a size that can no longer fully occlude the solar disk. Every total solar eclipse will have become an annular one instead. A ring of sunlight visible around the moon's edges. Impressive but fundamentally different. The geometry of coincidence finally broken by the slow arithmetic of orbital recession. This is, in the grand scheme of planetary evolution, a minor change. But it is a visible human-scale marker of a process whose deeper consequences are anything but minor. The day will continue to lengthen. Earth's rotation, already slowed from the original 6-hour period of the post-impact world to our current 24 hours by 4.5 billion years of tidal breaking, will continue to decelerate as long as the moon exerts tidal forces on Earth's oceans. The rate of deceleration will change as the moon recedes. Tidal forcing weakens with distance. So a more distant moon breaks Earth's rotation less efficiently, but the direction does not change. The day grows longer. In several hundred million years, a day may stretch to 25 hours. Over a billion years, projections suggest days of perhaps 30 hours or more, depending on how ocean configurations, continental arrangements, and tidal dissipation rates evolve through geological time. These numbers carry real uncertainty. The efficiency of tidal dissipation depends on the geometry of ocean basins, which change significantly as plate tectonics redistributes the continents, and these future configurations are not precisely predictable. But the direction is certain, and even the conservative projections describe a significantly different rotational regime than the one life on Earth currently inhabits. A longer day means a different climate. Not catastrophically, not immediately, but in ways that compound across geological time. The length of the day influences the depth and intensity of the atmospheric boundary layer, the temperature differential between day and night, the large-scale circulation patterns of the atmosphere. A 30-hour day gives the sun more time to heat the surface before the planet rotates away from it, deepening the daily temperature cycle. It changes the timing and character of convective systems, the development of weather patterns, the distribution of precipitation. These are not changes that eliminate life. Life has demonstrated across the history of this planet a capacity for adaptation that exceeds every reasonable expectation. But they are changes that reshape the ecological landscape, that alter which environments are hospitable and which are not, that demand continuous evolutionary response from every lineage they affect. The tides will weaken. As the moon recedes, the tidal forcing on Earth's oceans diminishes with the cube of the increasing distance. A moon 10% farther away exerts tidal forces roughly 27% weaker. A moon 20% farther away reduces tidal amplitude by nearly half. The intertidal zones that line every coastline on Earth today, those ecologically rich, biologically productive strips of substrate exposed and submerged by the rhythmic passage of tides, will narrow. The tidal range that currently floods and exposes many coastlines by meters each day will compress toward the modest solar tidal effect that would persist even if the moon were entirely absent. The coastal ecosystems built around tidal amplitude, the salt marshes and mangroves and rocky intertidal communities whose entire architecture depends on the predictable rhythm of flooding and exposure, will face a fundamentally altered regime. Some will adapt. Some will shift toward configurations better suited to reduced tidal energy. Some, in regions where tidal amplitude is already near the threshold for the ecosystem processes that sustain them, may simply lose the physical driver that maintains their ecological character. But the deepest consequence of the moon's recession is neither the day length nor the tides. It is the tilt. As the moon moves farther from Earth, the stabilizing torque it exerts on Earth's axial bulge diminishes. The gyroscopic damping that has kept Earth's obliquity cycling within a relatively narrow range for billions of years gradually weakens. The same gravitational perturbations from Jupiter and Saturn that, on a moonless Earth, would have driven the axial tilt into chaotic excursions become progressively less constrained by the moon's influence. Current models suggest that this effect does not become significant on short timescales. The moon's recession over the next several hundred million years may not meaningfully alter the obliquity dynamics that have governed Earth's ice age cycles and long-term climate patterns. But over timescales approaching a billion years, as the moon retreats to distances significantly beyond its current orbit, The stabilizing influence weakens to the point where the system's behavior may become qualitatively different. The tilt that has cycled reliably between approximately 22 and 25 degrees for billions of years may begin to migrate more broadly, exploring regions of obliquity space that Earth has not visited since before the Moon existed. This is the eerie closing of a loop. The first Earth before Theia's impact spun fast and tilted freely, a world without a gravitational governor, subject to the chaotic wandering that a large natural satellite prevents. The last Earth, billions of years from now, may not spin as fast, but as its moon recedes toward the threshold of meaningful stabilization, the axial behavior that made the pre-impact world so inhospitable to complexity may begin to reassert itself in slow motion. The conditions that the Theia impact created, the stabilized tilt, the moderated spin, the powerful tidal forcing, are not permanent achievements. They were set in motion by a collision 4.5 billion years ago and have been gradually, continuously evolving ever since. The moon's recession is not an ending in the way a catastrophe is an ending. It is a slow unwinding, a dissipation of the original energy investment made by Theia's impact, the system moving toward a lower energy configuration that happens to be less hospitable to the kind of life that emerged while the energy investment was at its height. None of this unfolds in isolation. The moon's recession is not the only process reshaping Earth's long-term future. The sun is brightening. Main sequence stars increase their luminosity as they age, as hydrogen fusion in their cores gradually increases the mean molecular weight of the core material and compresses it to higher temperatures and densities. Over billions of years, this increasing luminosity represents a slow but relentless increase in the energy input reaching Earth's surface. The planet's long-term climate depends on a balance between incoming solar energy and the rate at which Earth radiates energy back to space, modulated by the greenhouse effect of its atmosphere. As the sun brightens, maintaining that balance requires reducing the atmospheric greenhouse effect, something the slow geological process of carbon cycling through silicate weathering does, drawing carbon dioxide from the atmosphere over geological timescales as higher temperatures increase weathering rates. But this buffering mechanism has limits. The silicate weathering feedback can only draw atmospheric carbon dioxide down to the minimum levels that support the photosynthetic organisms that run much of the planet's biological carbon cycle. Below that threshold, the biological machinery starts to fail. Current projections suggest that photosynthetic life on Earth may face a hard limit from this mechanism within roughly 1 billion years. Not because the sun explodes or the planet is struck by another impactor, but because the slow, quiet brightening of our star will eventually outpace the geological carbon cycle's capacity to compensate. 1 billion years from now, then, Earth may face a convergence of stresses. A more distant moon providing weaker tidal forcing and less axial stability, a brighter sun pushing surface temperatures toward the threshold of ocean evaporation, and an atmosphere whose carbon dioxide has been drawn down so far by increased weathering that photosynthesis struggles to maintain itself. These are not independently catastrophic timelines. Each taken alone unfolds slowly enough for evolutionary adaptation to track it, but their convergence describes a future Earth that is meaningfully different from the one we inhabit. One where the long equilibrium of the past several hundred million years, the stable temperate zones, the moderate seasons, the rich coastal ecosystems, the biological productivity that has sustained complex life through 5 mass extinctions and counting, begins to erode in ways that may be irreversible on any timescale that matters for complex life. It bears sitting with this for a moment. The window of time during which Earth has been genuinely hospitable to complex, differentiated, cognitively sophisticated life is not infinite. It had a beginning, approximately 500 million years ago, when the Cambrian explosion of complex body plans transformed what had been a microbial world into a world of ecological architecture, comparable in its basic outlines to the one we inhabit today. And it has an end, somewhere in the range of 1 billion years ahead, set not by any catastrophe, but by the quiet arithmetic of stellar evolution and orbital mechanics working together. We exist in the middle of that window, not at its beginning, not near its end, but somewhere in its generous middle, in a period of stability and biological richness that the physics of the Earth-Moon-Sun system has permitted for an interval that, vast as it seems in human terms, is finite in cosmic ones. The moon's recession, the sun's brightening, the eventual loss of conditions favorable to complexity, these processes will continue whether or not any conscious entity remains on Earth to observe them. The last tidal flat that once thrummed with biological productivity will become a mud flat, then dry land, then eroded stone, long after the organisms that evolved to exploit tidal rhythms have either adapted into something unrecognizable or disappeared entirely. The day will lengthen, the eclipse geometry will shift and then fail, the tilt will wander, the oceans will eventually begin their slow journey toward an atmosphere thick with water vapor and thin with carbon. And the planet will, in certain measurable ways, resemble its own past, a world spinning in a different relationship with its sun. A world whose gravitational companion, still present but now distant, no longer governs it the way it once did. A world, in the deepest structural sense, moving back towards something like the chaos that preceded the arrival of the moon. The first Earth died in a collision so that ours could live. The last Earth will not die in a collision. It will simply, slowly over timescales that make the entire history of animal life on this planet look brief, lose the conditions that the collision made possible. The moon's arrival was violent and sudden. Its departure is gentle and interminable. But both ends of the story are written in the same physics, the same conservation laws, the same orbital mechanics that govern every gravitational system in the universe. Ours is one story of many, but a remarkably lucky one. Go back to the beginning, not of this film, but of the question it asked. An Earth without a moon. A night sky emptied of its most familiar presence. When we posed that image at the start, it was designed to unsettle, to make you feel the absence of something you had never consciously valued, but you did not yet know what the absence really meant. You did not yet know that the moon's removal would take with it the stability of the axial tilt, the depth of the tides, the length of the day, the chemical productivity of the intertidal zone, the long climatic continuity within which 4 billion years of biological elaboration could quietly accumulate. The empty sky was a thought experiment. Now it is a statement about physics, and the distance between those two things is the distance this story has traveled. Let us close the loop. There was a first Earth, spinning fast in a young and violent solar system, tilting freely without a gravitational governor, generating tides too weak to fully exploit the chemistry simmering at its margins. That world was not dead. It was not without promise. Not. But it was unstable in the specific way that matters for complexity. Unable to offer the long, patient, generationally continuous stability that sophisticated life requires to build itself out of simpler precursors. That Earth was a draft, rich in raw materials and energy, missing only the architectural element that would have allowed those materials to be organized across geological time into something more than simple chemistry. Then a planet the size of Mars arrived at the wrong angle and the wrong speed to be avoided, and the collision that followed was not, by any reasonable prior reckoning, destined to produce the outcome it produced. The parameters that yielded a stable moon in a stable orbit around a transformed Earth occupied a subset of the physically plausible space of outcomes. Not an impossibly small subset, but not a guaranteed one either. The moon is not inevitable. It is a result. From that result came the slow lengthening of the day, the damping of axial chaos, the enormous tides of the early Earth crashing across intertidal zones where chemistry cycled between concentration and dilution on the moon's orbital schedule. From those tides came perhaps the first experiments of molecular self-organization. From those experiments came eventually cells. From cells came everything that has ever lived on this planet. Every microbe in every forest, every reef and every extinction event that cleared the ecological ground for something new. Every lineage that developed eyes and legs and nervous systems of increasing complexity. Every organism that ever modulated its behavior in response to the phase of the moon without knowing what the moon was. And from all of that eventually came a species capable of launching itself off the surface of the Earth, landing on the moon and bringing back samples of the object that made it possible. The loop closes in the lunar dust, in the bootprints left by creatures whose existence the moon helped to architect. Now the moon is leaving. The same tidal friction that built the conditions for complexity over billions of years is slowly dissolving them, transferring Earth's rotational energy into the moon's orbital energy in a transaction that moves in only one direction. The day will lengthen. The tides will weaken. The axial stabilization will gradually relax. Over timescales that exceed the entire prior history of animal life on Earth, the conditions that the Theia impact created will slowly erode. Not catastrophically, not suddenly, but with the quiet, inexorable arithmetic of orbital mechanics working across deep time. The window of maximum habitability, the window within which the combination of moderate rotation, stable tilt, powerful tides, and temperate climate all operated together in a configuration favorable to the emergence and elaboration of complexity, is not infinite. It had a beginning in the aftermath of a collision. It will have an end in the slow recession of an orbit. You exist in its middle. What does this mean for the universe beyond our system? The question is not rhetorical. If the moon's presence was critical to the development of complex life on Earth, not sufficient alone, but perhaps necessary in the sense that removing it from the equation produces a planet less capable of sustaining the long-term continuity that complexity requires, then the distribution of large moons around Earth-like planets becomes one of the most consequential variables in any honest accounting of life's cosmic prevalence. We do not yet have a reliable census of exomoons. The detection of moons around planets orbiting other stars is at the edge of current observational capability, and the data we have is sparse. What we do know is that the configuration that produced our moon, a large impact during planetary formation delivering a satellite of just the right mass in just the right orbit, is not guaranteed by the standard dynamics of planetary system formation. Some worlds will have it. Many may not. The universe may be full of planets with liquid water, with carbon chemistry, with all the ingredients of biology, where complexity never quite achieves the stability it needs to build itself past a certain threshold. Because no Theia ever arrived at the right angle, or arrived but hit too hard, or grazed past without leaving a companion of sufficient size. Dead drafts circling their stars in conditions that are almost right but not quite, missing the moon moment that would have turned almost into actually. Or perhaps there are other paths. Perhaps tidal locking to a nearby star can provide rhythms that life entrains to without a moon. Perhaps binary star systems offer their own stabilizing dynamics. Perhaps the universe has solved the problem of complexity through mechanisms we have not yet imagined, on worlds configured so differently from our own that the frameworks we use to think about habitability do not apply to them. We do not know. The honest position is that we have one example of a living world, and that world has a moon, and the moon appears to have mattered. What we cannot yet say is how often the universe produces this arrangement, and what happens on the vast majority of worlds where it does not. But you are not on those worlds. You are here on this one, in the particular sliver of time when the Earth-Moon system is configured within the range that sustains minds capable of recognizing themselves as products of that configuration. That is not nothing. It is, in fact, the only reason this question is being asked at all, because the conditions that allowed you to exist also allowed you to become curious about the conditions that allowed you to exist. The loop closes not just geologically, but cognitively. Matter organizing itself into a pattern, capable of asking where the pattern came from. Think about what you are, stripped of everything incidental. You are the endpoint of an unbroken chain of survivors stretching back 4 billion years, every single link of which managed to reproduce before dying in an environment that was continuously trying to kill it. Every extinction event that ended the majority of species on Earth, and there have been at least 5 that erased more than half of all complex life, failed to end your lineage. Every ice age, every volcanic winter, every asteroid, every shifting ocean chemistry, all of it failed to sever the chain that leads to you. And the frame within which all of that surviving occurred, the climate stability and tidal productivity and axial regularity that made a complex biosphere possible in the first place, was built by a collision you were never taught to be grateful for. Every time you see the moon, you are looking at the debris field of your own origin. Not metaphorically. The material in that gray, cratered surface was once part of this planet, was vaporized and ejected by an impact so energetic it partially destroyed 2 worlds, and accreted over thousands of years into the body now orbiting overhead. It is older than any rock on Earth's surface. It carries in its isotopic composition a memory of the violence that produced it, and it has been returning that violence as stability ever since, moderating the spin, damping the tilt, pulling the oceans into tides, keeping this planet within the narrow envelope of conditions where 4 billion years of chemistry could eventually produce something capable of looking up. You are what happens when a planet gets a second chance. The moon will not be there forever. Its light over the ocean tonight is borrowed time. Billions of years of it still remaining, but borrowed nonetheless. The tides rolling beneath it are still strong, still productive, still running on the angular momentum budget set by the Theia impact in the deep past. The creatures living in the intertidal zone are still timing their reproduction to the same 29-day clock that the first organisms in tidal flats were entrained to when the moon was young and enormous in the sky. The chain is unbroken. The window is still open. And within it, matter has somehow arranged itself into a form that can wonder at its own contingency, that can trace the story from a molten planetary collision to a conscious mind, and find in that story not just explanation but something approaching awe. How many other moons are out there, waiting to turn dead worlds into places where something like you can wonder why?